Barry here. So today we're going to have a quick look at surface area to volume ratios and how they affect areas such as biology and chemistry. Now, if you are a fan of mathematics, then odds are you have probably already come across stuff like this before. However, if you're not and you're still a little bit confused by it, don't worry, I'm going to go through it step by step so that you can become a master at it. So let's have a look. Imagine that there are two blocks of wood. Each one is 20 centimeters long by 20 centimeters deep by 20 centimeters high. And we're trying to burn them. Now, you are about to burn your piece of wood, but you decide to do something a little bit different with it. You decide to cut it up into small pieces because you know that smaller pieces burn faster. So you take a saw and you cut them into 10 by 10 by 10. So each piece looks a little bit like this. So you have 10 centimeters by 10 centimeters by 10 centimeters. And of course, there's 8 of them. All right? So if that's the case, then odds are your pieces are going to burn faster. My question to you is, why? The simple reason, ratios. Now, if you've ever done maths and you've had to look at surface area and volume in terms of geometry, as well as looking at rates and ratios, both of them are going to apply here in a real-world application. So, let's calculate the surface area for each set. Here is my block of wood. It's 20 centimeters long by 20 centimeters tall, so that's one side. Since it's a cube, all of the sides are the same size. So naturally, it's going to be times by 6 to equal 2,400 centimeters squared. Okay? That's the first part. The next part is we're looking at yours. You have a 10 by 10 surface here. There's 6 of them for that whole cube. Now we times that by 8 because that makes up the total amount that you have here, which equals 4,800 centimeters squared. Already there's a bit of a difference. The difference is caused by the surface area that's exposed inside the blocks. So if I had them stacked like this and I painted all the outside and then later on I took them apart, you can already guess what would happen. Half of the cube has been painted, the other half that's inside the cube hasn't. Okay, this is important. In order for chemical reactivity to happen, it needs to make physical contact with the surface of the material. Now, if I have my block here, all of the stuff on the inside hasn't been touched yet because there's no way for the chemicals to get in. It has to slowly erode the outside, then go into the next layer. It's almost like having an onion, okay? If I have an onion and I cut it into pieces, then I can see all of the layers that it interact with, as opposed to peeling one layer at a time. Well, let's look at their volumes. Our volume is calculated by the width, by depth, by height. So 20 by 20 by 20 gets us to about 8,000 centimeters cubed. The exact same volume as this one. Remember, solid objects do not change their volume. In fact, they don't change much of anything, really, because the atoms are so heavily linked together. So, these two are the exact same size, the only difference is one has been broken up into small pieces. Okay, the same amount of materials there. Now, if we start comparing these as our surface area and volume ratios, we have 2,400 to 8,000. I'll divide both of them by 800 because I want to simplify this. I want to make it the simplest version of this ratio that I can. So that gets us around about 4 to 10. That gets us around about 2 to 5. And eventually, it's a 1 to 2.5 ratio. So, it's average, okay? Compared to the one over here, though, it's quite different. Surface area to volume, 4,800 to 8,000. Divide both by 800. That's around a 6 to 10 ratio. That gets us to a 3 to 5 ratio. That gets us to a 1 to 1.67 ratio. So, in comparing these two, which ratio is bigger? This one. This one is bigger. Now, if it's bigger, that means it's going to be less reactive. Reason why? is because there's not as much surface area compared to the volume, which means that there's less chance of material interacting with it. So you toss yours in the fire, all of the air is going to be able to go in between these cracks and start burning the material. Mine has to wait until the outside layer's fallen off, then it goes on to the next layer inwards, and so on. It's much slower. How this applies to biology and chemistry is simple. If you have a smaller sample size, or you have a smaller sample object, I should say, then naturally it's going to react faster with the water around it. Your cells are really small because they need to react quickly to any changes. If they run out of water, you need to get rid of that water and collect new water. If they run out of oxygen, they need to get rid of the carbon dioxide and take in more oxygen. Okay, and so on and so forth. If your cells were bigger, they start to die because they can't get the material quick enough. Let's use another comparison. Let's say you have a polar bear and you also have a bilby. For those of you who are not from Australia, a bilby is a small marsupial not unlike a rabbit. Which one of these animals do you think is better suited for a desert environment? If you said the polar bear, you're going to lose your money. Polar bears have a very, very large surface area to volume ratio for their size as an organism. For this reason, they can't release heat into their environment very quickly. As a result, they can overheat very quickly. So they're better suited for a cold environment. Bilbies, on the other hand, are very, very small. They have very large ears. So they have a very small surface area to volume ratio, which means they're able to release heat very quickly and they're better suited for a hot environment. You want another example? Here's one. Imagine a city. Now imagine that city without any roads, trains, highways, subways, overpasses, or footpaths. How quickly could you get food and water into the city or out of it? Answer? It would be very, very slow. Because of this, cities need effective infrastructure, which is the ability to transport materials very quickly throughout an area. Same way that blood vessels are spread out effectively throughout a body. If they're all clumped in one area, then that means they're probably going to miss a whole bunch of cells in another area. And if they miss those cells, then they can't transport materials to them very, very quickly. Okay. What I would like you to do, if you have a chance, is to do this activity again, but imagine a box with, or imagine a different shape with different volumes and surface areas. So if you're unsure, do a cube. If you want to do something a little bit different, you can. I'm not going to stop you. But make sure you have a go at calculating surface area and volume for each of them and then converting it into a ratio. Okay? Make sure you double check your work. Ask your teacher if you've got any questions about it. And just make sure you've got this biochemical maths nailed down. As always, I've been Forry. You've been amazing. I'll see you around.